This will serve as our review/overview on torque. The ability of a force to cause rotation depends on three factors. One is the magnitude of the force. The stronger the force, the larger the torque. Two, the distance r from the point of application of the force. Basically, the further away from the pivot point that you apply the force, the larger the torque. We'll take a look at some examples of this in a moment. And three, the angle at which the force is applied. So here are some examples. Here we have the top view of a door, so we're looking down on the door Superman style. The hinge is on the left, and we've got four different forces being applied here. Force 1 is being applied almost at the far edge of the door, so this is at a pretty large distance away from the hinge here. It's being applied at 90 degrees, so this is going to result in a pretty large force. Force 2, however, if you think about it, if you try and push on the door this way, it's not going to open, it's not going to close. You're just wasting your time at this point. So this angle, basically 180 degrees or 0 degrees away from the door, is pretty ineffectual, and that's going to result in a torque of 0. If you think about pushing at the same point as force 1, but at an angle like force 3, you're going to end up with some torque. That's going to move the door slightly, but not nearly as much as if you had pushed directly on, as in force 1. And lastly, if you push close to the hinge, so at a small distance away from the pivot point, it's going to be more difficult to open or close the door. It's going to be harder to rotate the door around this pivot point if you push with equal force close to the edge of the door versus further away. If you don't believe me, try it for yourself. So let's take a look at mathematically how this works. So here we have a wrench, and it is going to turn this bolt or washer here. And we see that there's a force applied in this direction. That force is applied at an angle with respect to the r vector here. So r starts at the pivot point, travels out to wherever that force is applied. So this is the distance r, and the vector continues pointing on this direction. So out of the page. So the angle between that r vector and the force vector, we're going to call phi at this point. If it is counterclockwise, so in the direction that I have shown here, from r to f, then that's going to give us a positive torque. So we want to look at mathematically how we calculate torque. Torque is a vector, so here I've got my vectors as bold. So torque is defined as the displacement vector r crossed with the crossed with the force vector, and that's going to have units of newtons per meter. We want to look at just the magnitude of this force. Then that is going to be the distance from the pivot point to the point where the force is being applied, times the strength of the force, times the sine of the angle between the r vector and the force vector. If we have torque that causes a counterclockwise motion, then that torque is going to be positive. The opposite is therefore also going to be true. If you have a torque that causes a clockwise motion, that is going to be a negative torque. So moving backwards to our previous slide, this force right here is going to cause this wrench to move in a counterclockwise fashion. So that means that this torque is going to be a positive torque. Now, we can see how the different angles of the applied force can change what the torque is going to be. So we'll start with this one here. At this point, if you apply a force at this pivot point in this direction, that is going to give us the maximum positive torque. So our angle here is 90 degrees. Actually, it's from here to here is 90 degrees. So sine of 90 is 1. And since it is going to cause rotation in the counterclockwise direction, that's going to be a positive torque. Now the force right here, this is an angle slightly less than 90 degrees, something like 45, from the r vector and the force vector. So that is also going to cause a counterclockwise rotation around the pivot point, but the magnitude of the torque is going to be smaller than in this particular case. Now, trying to pull out on the wrench or push in on the wrench is not going to cause any torque. There's going to be no rotation at that point. So the torque in those cases is zero. If we take a look at this force right here, the angle we'd be looking at would be the angle from the R vector, so starting at the pivot point and working its way out. That's the R vector. The angle from there to the force, which here is roughly 45 degrees, will determine the amount of torque. And since this is going to cause a motion in the clockwise direction, that's going to be a negative torque. And here, this force right here would be the maximum negative torque. Again, it's perpendicular to that R vector, but it's going to cause a clockwise rotation, therefore giving us negative torque. So, as we've already seen, or as we've already discussed when we saw this figure earlier, torque is going to depend on the particular point at which it is applied. Now, mathematically, this is because it depends on the distance from the pivot point to where the force is applied. But conceptually, you can get the idea that pushing at this point on the door with a force of 2 newtons is not going to rotate very much, whereas pushing it at this point with a force of 2 newtons is going to cause a much larger rotation. So, the place at which the force is being applied does make a difference. Now, here's a question that you all can take a moment to think about to yourself, and when we come back, I'll go through and explain the answer. But pause the video, try and figure out if you can come up with the correct order on your phone. Okay, so let's go ahead and see if your answer is correct. So as we go through and look at these, we can, from practice, kind of tell that some of these are going to be larger than others. For example, this one right here, this is going to be the smallest amount of torque because that's going to have a torque of 0. Basically, pulling on this handle is basically going to cause no rotation, so that's going to be the smallest. If I compare these two, I can see that A is going to cause a larger torque than B, simply because the force is applied at a larger distance away from that pivot point. The amount of the force is the same, but since this right here is a larger distance than here, that means the torque of figure A is going to be larger than the torque of figure B. Now if we compare figure A to figure D, here in figure A we've got a force of 2 newtons, the full length of this handle, and here we have a force of 4 newtons applied at half the length of the handle. So if you think of this distance as being R, this is going to be 2 times R, whereas this is going to be 4 times R divided by 2, which still gives you 2 times R. So A and D are actually going to be equal. And this makes sense. The closer in to the pivot point that you push, the more force you have to apply in order to get the same results as what you do with figure A. So far, we have A and D are equal, B is the next smallest, and C is the smallest. So let's see how E fits into this. At this point, we have 4 newtons of force times the full length here of our handle, we'll call that R, but now we have an angle, so we're going to have this multiplied by sine of 45. If you plug it into your calculator, sine of 45 is about 0.7. 0.7 times 4 is going to give you a result that's still going to be larger than 2. So your answer is going to be larger than 2 times R, so that means E is going to be larger than A. So the correct order from largest to smallest is the torque of figure E is larger than the torque of figure A, which is equal to the torque of figure D. Next smallest is the torque of figure B, and the absolute smallest is the torque of figure C. Now, if you do have more than one torque being applied on the same object, the net torque is going to be the sum of all the torques of the object. So back to our example of the door, let's go through and look at what the magnitude of the torque is due to each one of these forces, starting with 1 and working our way through 4. So, torque 1, which is due to force number 1 times the distance from the pivot point to where it's applied, which we're going to call R1, times the angle between those two. That's a 90-degree angle. So this gives us R1 F1. If we look at the torque due to force 2, since this is pointing anti-parallel to the object here, to our R vector, basically our angle is essentially 180 degrees. Sine of 180 or sine of 0 is just going to be 0. So this force gives us no torque. 3 should be the same as F1, but with the angle applied here. And the thing you're going to want to be careful of is which angle are we talking about. So again, it's from the R vector to where the force is applied. The force is applied at this point here. You can either draw it pointing into the object, as you might think you would actually do if you're pushing it, or it would be equivalent to say it comes out in this direction. Either way, I'm going to estimate that the angle is roughly 45 degrees. And lastly, for F4, this is a 90-degree angle. So we have the distance from the hinge to the point of application, which I'm going to call R sub 4, and the magnitude of the force there. Now, the distance from the hinge to this point here, the point of application of both forces 1 and 3 is the same. Now I'm going to estimate that you need roughly 4 of these distances to equal 1 of these long distances. So basically that R4 is 1/4 of R1. Also, by looking at the length of each of these vectors, I'm going to say that the magnitude of each of these forces is 0. So now I can start to look at exactly how the net torque, the net rotation on this door, what that might be. So my net torque is going to be the torque from force 1. Again, the torque from force 2 is 0, so I'm ignoring that. The torque from force 3, and the torque due to force 4. Since my distances R1 and R3 are the same, and R4 is basically 1/4 of R1, and my forces are equal, I can start to simplify this. So now all my forces are the same, and I have substituted in for R3, I've substituted in R1. For R4, I've substituted in R1 divided by 4. Now I can start to add this up. If I pull out R1 F1 from this, I get 1 from here, 0.25 from here, so I can think of 1.25. And sine of 45 is approximately 0.71. So if I add that up, oops, that's not 1.96, that's actually 1.96 times these forces. So sorry for the typo. So the more forces I add, the larger or smaller the net torque might be. All of these forces, if they end up applying any torque, they're applying all positive torque. If I had a force, say example, that was pointing downwards, someone else was on the other side of this door pushing in the middle, that would be a negative torque, so you would want to subtract that from the net torque.